let's talk about math proofs for a little bit. So there's this idea of something called a monotone convergence theorem. And the monotone convergence theorem is a really neat theorem that basically says, look, if I know that you are always moving up, but I know that you'll never move up past a certain amount. So you're always going up, but you'll never go up past a certain amount. Then I know that you must converge to some value. You must plane off and converge. The reason why that has to happen is because you're not coming down. So if I know that there's a ceiling up here, then you've got to basically go and hit that ceiling. But if by definition you can't go above it, I know you can't shoot off to infinity, and I know you can't shoot down to infinity because you're always increasing. So you're increasing towards that ceiling and then you plane off. And there's a little more to it, but the idea of the monotone convergence theorem is really neat because it basically says, look, you're going up, buddy, but you're not going any further than this, so you got to stop somewhere. And I know you can't oscillate or anything like that because you're always increasing, so you can't wobble away. You just have to. It's almost like the squeeze theorem, just getting you in. So more formally, what we can say is if a sequence is monotonic, what monotonic just means is that the sequence gets either each term is at least as large as the old one. Oftentimes for sequences it won't be just at least as large, it'll be strictly increasing, but sometimes it's not true. Or if it's strictly decreasing, so it's always going down. If it's one of those and it's what's called bounded, so something is bounded above if there's an upper limit. It may not even get this big, but it definitely won't get bigger, right? You could have a ceiling. If this is your ceiling, then this number is also your, well, I'm going out of the frame, but if this is a ceiling, then this number is also a ceiling, and this number is also a ceiling, because if it can't get this high, it definitely can't get this high. And so it's bounded above if it says, look, the sequence is never going to get any higher than this. And then if it's bounded below, meaning it's never going to go below this certain value. So a sequence is considered bounded if it's bounded above and below. So you kind of have this window that says, this sequence is only going to be between these two numbers, period. It's never going to be outside this window. And if it's like that and increasing and decreasing, then you know it's got these finite limits that it has to stop at, and it's going to converge. So that's a really neat, really neat and important result, and it's leveraged in so many applications. It's used also when we get to the idea of series. We use the monotone convergence theorem, but beyond that, there's a lot of mathematical applications that use this type of theory to understand whether something stabilizes or doesn't. So anyway, the way you do this is you say, okay, well, I need to know if a sequence is increasing or decreasing. Well, how do I do that? If only there was something in calculus that we did that helped us to determine if something was increasing or decreasing. Of course we did. We came up with the idea of a derivative, right? So these are discrete. These take on finite values. But if the continuous function is also monotone, or monotonic, either one of those is fine to say. If the continuous function is also monotone, then the discrete samples of that function will also be monotone. So what we can do, this isn't the only way, this is what's called a sufficient condition, but it's not necessary to do it this way. So let's take a look at this. It says, all right, I'm going to define a function f of x 6x over x plus 4. And then I am going to take its derivative. I'm going to say f prime of x is that x plus 4 times 6 minus 6x times 1 over x plus 4 squared by the quotient rule. And that gets me 24 over x plus 4 squared. So if I look at this, I say, okay, well, for And remember that for the sequence, we're only considering the positive integers. So we're never going to have like a -4 in there, so it's never going to blow up. X is always going to be 1 or greater. Well, if you look at this, well, what's squared on bottom is always going to be positive. So this is always greater than 0. So what did we learn about the fact that if the derivative is positive, then the function is increasing? So it's increasing on the entire domain. So we know that it's monotone increasing. Now the question is it bounded? Is it bounded? How would we know if it is in fact bounded? Well, what we need to do is we need to say, okay, this function is increasing on 1 to infinity, but does it have a maximum? Does it? Well, another way that might be better is instead of, there are a few things we could do, but why don't we do something like rewrite this function in a way that makes more sense? If I do long division here, what I'm going to get is (6 minus 24 over x plus 4). So, oops. I'm so sorry. I was wondering what went wrong there. That's -24. So it's decreasing on 1, 0. The reason why I want to say that is because, okay, it's decreasing. So it's always decreasing. Now that means that if it's always decreasing, it has to be bounded above by the first term. Has to be. So it can't be any larger than that because it's always decreasing. So it's bounded above. Now is it bounded below? So how do we figure out if this is bounded below? Well, if you take a look here, so in this case don't look here. In this case we're only ever plugging in positive numbers. So these two numbers are always positive. It's positive on top, it's positive on bottom, which means it can never be negative. It can't be. There's no possible value that will make it negative. So that means that it is always greater than or equal to 0, and it is always less than or equal to 6/5, which tells me that it is bounded and decreasing. So in this particular case, it is both monotone and bounded, which guarantees me it'll converge. Now, we could clearly run the limit here and see that the limit's going to be 6. That wouldn't be a problem. But if we know it's monotone and bounded, we can just say, it's going to converge. And sometimes that's all that matters. You don't need extensive work to say, well, I have to get it down to this. All you care is that it's stable. You either care if it's stable or unstable. In a lot of systems, that's all that matters. You just care about stability. You say, is it gonna fall apart on me, or is it gonna keep working? All I care about is if it's gonna keep working. Now, in this particular case, n e to the negative n over 7, is it monotone and or bounded? So we need to define a function here. We have to say, okay, g of x is x e to the negative x over 7. So then I need to take a derivative. Say g prime of x is e to the negative x over 7 minus 1/7 x e to the negative x over 7. Hopefully you remember how to do all these derivative rules. So then I can factor this. I can say that is equal to e to the negative x over 7, 1 minus 1/7. 1 minus x over 7, which I can then, and probably better should, rewrite as 1 negative 1/7 negative x minus 7. So why would I want to do that? Why would I want to do that? Well, the reason I would want to do that is because I can show two things. I know that this is always negative. I know that this is always positive, right? So that's negative, that's always positive. But this right here, x minus 7, if x is less than 7, this is negative. So that means that that it's actually increasing it tells me that it's so if those two are negative, right? So that would cancel. So this g prime is positive. G prime is positive for the first 6 terms. It tells me that it increases for the first 6 terms. That tells me that after the 7th, so don't worry about the 7th, at the 8th term, G prime is negative, so it always decreases after that. So that means it goes up and then comes back down. Now, one thing you do know is that this is always greater than or equal to 0, because this is positive and e to something is always positive. So positive, positive. So it's going to be, so it's bounded below. Now, is it bounded above? Well, I have very clearly here that it increases, or it has a critical point and decreases. So if it increases, has a critical point and decreases, well then that's a maximum. That's the first derivative test. So by the first derivative test, it's a maximum. So as a result, that is bounded above. Now the question is it monotone? Well, we just said it goes up and then comes down. But the definition of monotone says it either always goes up or always goes down. So since it has a change in behavior, it is not monotone, but it is bounded. In fact, what you'll actually find here is that this limit of this sequence will go to 0. And the reason it does is because after this point, every other term is decreasing. And for a lot of times for sequences, it doesn't matter where it starts. It matters that as long as if after some point, doesn't matter which point, could be 100 million points in, if after 100 million points in, it becomes monotone and stays bounded, because if it's bounded for all of them, it's clearly bounded for that small piece. If it becomes monotone and it's already known to be bounded, it will converge. It doesn't matter. But we're taking the baby steps now. We're considering the whole sequence. But in practice, you don't care. You say, it became monotone. Okay, well then it's going to converge. So anyway, the point is this will converge to 0. And you could do that by finding the limit. But it's also important to note the monotone convergence theorem does apply here.